So let me start by thanking the organizers for providing me the opportunity to actually be with you remotely. This was not the initial plan, but the starting of the semester and my teaching duties have been modified over the summer, so we have to change plans. So today I will be reporting on a recent experiment we've performed at Institut in Palaiseau about the observation of atom pairs in the quantum depletion of weakly interacting Bose gases. So let me first acknowledge the people who've been doing most of the experiments. So Antoine Thénard, Gaëtan Hercé were PhD students, along with Jan-Philippe Burek and Alexandre Darroux, who is a postdoc who joined us a bit more recently. So I will be talking about pairs, and I would like first to remind you that there are many ways of producing pairs in both, ranging from high energy physics with positron electrons or parametric down conversion in quantum optics, and closer to cold atom physics during the collision of two BECs if you have the scattering halo of S-wave scattering with two atoms at opposite position on the halo which are correlated in momentum. Another example is dissociation of a diamond. So all these experimental observations are dealing with out of equilibrium physics, where typically you can somehow build a classical picture, semi-classical picture with two incoming partners colliding, having a nonlinearity, and then outgoing. And in these microscopic descriptions, you have both momentum and energy, which is conserved. I will contrast these experiments with what happens at equilibrium. And so there are several, let's say, emblematic examples of pairing mechanism which occurs at equilibrium. The first one deals with superconductors with the celebrated Cooper pairs, which form once again at opposite momenta, and as we all know, is fundamental in the origin of conventional superconductivity. And actually, the same kind of pairing mechanism also happens in both superfluids. And this dates back from the observation of superfluidity in liquid helium and the later theory that was developed by Bogolyubov in order to understand and capture these superfluid properties. So I would like to say a brief word about this Bogolyubov approach. So as regarding superfluid properties, one of the main predictions of Bogolyubov theory is the existence of a linear spectrum of excitation, of collective excitations, phonons, which gives rise to these fascinating superfluid properties. And as was, for instance, probed, I'm taking an example of a cold atom experiment again, but in many different type of setups. A different second, let's say, prediction of this theory is a microscopic description of the many-modi ground state. And that respect, Bogolyubov's work was then, let's say, expanded by Li Wang-Yang about 10 years later. And I would like to say a brief word about this microscopic description, which basically starts from considering two-body contact interactions. And therefore, in this interaction term here, you have, let's say, four operators for amplitudes, which I write K1 and K2, and then K1 minus K and K2 plus K to have conservation of momentum. And Bogolyubov approximation amounts to saying that most of the atom, almost all the atom, are in the single particle ground state, the BEC. And therefore, you can write this interaction term to first order by taking two atoms in the BEC, which enters this the collision. And so if I take, for instance, here just these two first operators, what we are left with is with the creation of a K minus K pair. So the quantum depletion, which is the depletion of the Bose-Einstein condensate induced by interactions at zero temperature, consists in a superposition of such atom pairs, bosons pairs, with opposite momenta. And this is where, in my opinion, it's rather different from what happens at out of equilibrium, because of course, since you can produce a pair with arbitrarily large kinetic energy, you would not conserve energy if you would try to build such a classical picture. And the reason is because, of course, all the atoms in the quantum depletion and the BEC are in the same single particle many-body ground state. And so it's really quantum fluctuations and interactions which gives rise to this pairing mechanism here at equilibrium. Well, so what has been observed rather recently in the group of Zoran Zibabic in Cambridge was to actually count how many atoms are quantum depleted, so the total number of atoms. And it was shown that this verifies Bogoliubov theory. But we have not yet any observation of the pairing mechanism and nor what kind of, let's say, properties these pairing mechanisms gives to the many-body ground state. And this is the, let's say, the objective of our recent work. And how do we do that? The idea is to measure two-body correlations in the momentum space. So this type of correlator that you see here, A dagger K prime, aka K prime. So why do we measure that? Basically because since Bogoliubov theory is a Gaussian theory, you can use a big theorem and decompose this two-body correlation in two parts. So a normal part and a so-called anomalous part. The normal part is the one which is also present in a non-interacting Bose gas. And this normal correlation has a peak located at K primes equal K, which means when two bosons are found close by. And this is nothing but the bosonic bunching, which is, of course, associated to the statistics of indistinguishable bosons. The second term, the second part, the anomalous correlations are non-zero only for K primes close to minus K. And this, of course, is related to the presence of a pair K minus K, which is associated to the quantum depletion. So how do we measure this type of two-body correlations? Well, we are using some kind of special atom, a metastable helium atom, and let me walk you through the experimental part. So we are working with metastable helium atom, helium-4 atoms, and we are producing BECs in this metastable state here in orange, which has a very large internal energy of about 20. And this energy is sufficiently large that if you let your atoms initially trapped up there fall onto a metallic plate, the metastable atom can go to its ground state and extract one electron by releasing its internal energy, extracting one electron from the metal. And so if you are capable of amplifying the electronic signal, then you are able to detect atoms one by one. What is more is that actually the detector, which looks like that, so you have this disk here, which is called a microchannel plate, and below we have a so-called delay line anode, which allows us to not only detect atoms one by one, but measure the position x, y in the plane of the detector and the time of arrival. So therefore, we have for each individual atoms the three coordinates. And as you will have guessed, because we are letting the atom fall over like half a meter, so for a very long time of flight, the gas expands with its initial velocity. And so therefore, the three-dimensional coordinates that we measure with our detector is the initial velocity of the atom. So we thus access three-dimensional momentum distribution, single particle resolved. So let me say a little bit more about this experiment I'm reporting now, is that actually we are loading the BEC in a 3D optical lattice, so a simple cubic optical lattice, and therefore realize this Bose-Bart model. And I would just want to remind you about these two energy scales, so the tending amplitude J, which I will be using in the following, and the on-site interaction U. So why do we use an optical lattice here? Well, the reason is twofold. I will not expand onto it. But the first one is that if you let an atom expand, if you let a gas expand from an optical lattice with one atom per lattice site in average, then you can really measure the intrap momentum distribution after time of flight. And this was, I mean, you have an example here of a momentum density, which is plotted in log scale as a function of momentum. And you have a comparison of experimental signal with an initial quantum Monte Carlo calculation for the intrap momentum distribution. So you can find like more details in this 2018 paper there. So this is the first reason. The second reason is that, of course, we can tune the ratio U over J, and we can go from a superfluid to a Mott insulator. But within the superfluid, we can increase the interactions. And because the quantum depletion depends on interaction, we can, of course, crank up the effect and being able to, hopefully, to detect these pairs. So this is the way we do the experiment. So let me now report about this, some observation of those pairs. So I will be presenting experiments which are conducted deep in the superfluid regime. So U over J is 5. Here you have an example of a momentum distribution in 3D, which is three-dimensional. And each tiny blue dot, which is zoomed here, is a single atom. So you see that it's a superfluid because we have the famous diffraction peaks. And what our three-dimensional detection also allows us to do is to separate the condensate, which corresponds to one of those peaks, from the depletion. So we can really, they nicely separate in the weakly superfluid regime in the momentum space, and we can compute two-body correlations independently in the BEC or in the depletion. So I will be reporting about measurement in the depletion. So this is the momentum density as a function of momentum. And we will be calculating the correlation here in this green volume, where, in linear scale, it looks like there is nothing. But if you look in log scale, which is now here, you see that there is some signal. And here you have the anomalous correlations, which is plotted. So it's the type of correlation which should reveal the presence of pairs, which is plotted as a function of k plus k prime. And so as you see, there's a peak here, which signals the presence of atom pairs at opposite momenta. So we are very happy to see the signal. And the first thing that we wanted to do was to check that it was indeed very sensitive with temperature, as you would expect for the quantum depletion. So we repeated the experiment by heating up the BEC, and you have here the density profile in red. So in log scale, you see that we have increased quite a bit the depletion, but the condensed fraction stays about 30%. And in that case, we are unable to see any atom pairs. So I said in the introduction that you have two types of two-body correlations. So this anomalous correlation and the normal one associated to the benching. So we also, in the same data set, calculated the normal correlations. For instance, I'm plotting here two different temperatures again, the same ones. And you see that, contrary to the anomalous correlation, of course, the bosonic bunching is still there and nothing hardly changes. So this really is related to the bosonic statistics, why our anomalous correlation is related to the presence of atom pairs associated with the quantum depletion. So to finish, I would like to discuss a little bit the type of properties of the equilibrium state that we can infer from these measurements. And I would like to start from parametric down conversion. Imagine that we have like the perfect situation where we produce pairs of photons in two modes. So let's say that I label N1 and N2 with N photons, the same number in average. And now if I ask what is the probability to find coincidences of detecting a photon in 1 and in 2, well, it's the number of pairs, which is equal to the number in average to the number of photons in each mode, divided by the product of the two populations. So you see that the probability of coincidences should scale inversely with the population of the modes. And so we wanted to check something of this type because we also have this type of pairing mechanism. And what is the population here, the average population of the mode? In our case, it's the average momentum density. So we repeated our experiment by changing the average momentum density. And here you have plotted the peak amplitudes. So in green, you have the anomalous correlation, so the pairing. And in blue, you have the normal correlation, which means the bosonic bunching. And so as you can see, so first of all, the bosonic bunching, so what is plotted is the amplitude -1 in both cases. So the bosonic bunching is always equals to 2, even in the quantum depletion. And well, I could comment on that. We've published actually some work about this observation a few months ago. And what is more interesting is that you see that the anomalous correlation has an amplitude which indeed scales inversely with the momentum density. And so this is very analogous to two-mode vacuum squeeze state. And what is more is that since we have anomalous correlation amplitude, which is much larger than the normal one, this actually is a strong violation of the Cauchy-Schwarz inequality and therefore signal the presence of non-classical correlations, which is what you expect for the quantum depletion. So to go a little bit further, one can use actually this type of violation of Cauchy-Schwarz inequalities to infer some separable criteria and to quantify some entanglement in the form of separability, as for instance proposed in these works. And what we should do to be able to make such a statement about the fact that we have entanglement in the interacting Bose gas at equilibrium would need for us to look at this type of coherence. So the coherences between a mode at minus k and a mode at k. So in Bogoliubov theory, this term is predicted to be 0. So if we assume that Bogoliubov theory works, then our observation is sufficient to tell that we have some entanglement. Of course, what we want to do is to check this in the experiment before making any such statement. Okay, so let me conclude. So I've reported this the observation of these atom pairs in the depletion and of an interacting Bose gas at equilibrium. And I try to show you that one can characterize this interacting quantum state from looking at this atom-atom correlations. And this somehow also validates this approach of using a time of flight and single atom detection method, which is provided, for instance, by metastable helium, to further study and go towards more strongly correlated quantum states. And with this, I thank you for your attention.
Thank you. We have time for a question. I see but somebody has to pass the mic, and Piotr will be the second one.
Thank you for the talk. It was a very nice experiment, but I have some doubts about the theory, because what you've done is just a weak separation of the interaction term, and it could be done better with the extended Bose-Hubbard models. So my question is, what are the energy scales of the system? I mean the energy scales for the pairs and for the normal superfluid.
Okay, so let me first, well, maybe I can do that. So first of all, as you can see here on this picture on the right, so this is the momentum density measured in the experiment in semi-log scale as a function of momentum. So you see that the density in the depletion is really small. And what I can tell you is that the total depletion, so of course our system is at finite temperature, amounts to 10% of the total atom number. So we have therefore a quantum depletion which is rather small, and that we evaluate to be of the order of 5%. So this should be more or less in a regime where Bogoliubov approach can be thought to be reasonably correct. And so if you wish, the lattice here is very shallow. We are really far from the mode transition. And to answer your second question, maybe what I can tell you is that the momentum scale, which is on which this green area where we calculate two-body correlation is centered, it's typically centered for k times the Ealing length equals to 1. So the energy scale that we are probing is, let's say, around the clinical potential of the BC. So I don't know whether this answers your question.
Okay. Are you happy? Yes. So now, Piotr.
David, very nice results. I know a couple of groups have been trying to see these things for years, and so this is the first time I think somebody's seen this pairing and this depletion. I have a number of questions maybe, but I'll just ask one. I wonder, is it possible to do a dissipative Bose-Hubbard model in your lattice by, I don't know, introducing some sort of single particle dissipation or something like this?
Well, I can somehow easily think about introducing two-body losses. So we are working with a metastable state, and in order to avoid collision of two metastable atoms, because of course, you have two very high energetic atoms, what we are doing is we work with a spin polarized gas, and spin conservation forbids two metastable atoms from producing an ion and a ground state atom. So a trick that actually we have already played a little bit with is to do a spin flip or some like a Raman dressing of the spin polarized gas with a non-spin polarized one. And with the non-spin polarized one, you do have two body losses. So this could be a way of introducing, let's say, some dissipation. I don't know whether this, like two body losses, would be the kind of dissipation you would like to play with.
Well, there's lots of interesting ones, I guess. It's easy to play with single particle losses, I think, but two
Yeah.
particles also interesting things.
Okay. Okay. Are there any questions, comments? No? Oh, Piotr, you have again. Yeah, the last question of Piotr.
Okay, so maybe if there are no other questions, I'll ask the other question I was wondering. So I remember a couple of years ago, there was this effect that when there was no lattice, too much depletion was seen. And then this ANU group that I'm sort of involved with, they also saw too much depletion again. When you introduce the lattice, does that go away?
Well, you know, so what you are referring to is a BEC release from Harmonic Trap. When at the time we were looking at very large momentum tails. So in the lattice, we cannot access these types of tails simply because we are limited by the extent of a Brillouin zone. And then, I mean, everything is periodic. And so we have not seen anything, let's say, like this type of experiment that you are referring to. And I think mainly it's because we are not looking at the same momentum scales.
Okay, we have one question here online. So, Christian, can you unmute yourself and ask the question?
Yeah, sure. So my question is about, so could you measure like the temperature dependence of these correlations? So you showed two examples, right? But
yeah, we have more than that.
Yeah.
We have, let's say, 4 different data sets where we actually can look at what is the amplitude of the anomalous correlation as a function of, let's say, the Clement fraction or the temperature. Yes.
Right. Okay.
And of course, I mean, I didn't have time to show this, but so I've shown the 2 extreme case where we go from, let's say, 85% to 30%, and you completely lose the signal. But if you play with like 50% or 70%, then what you see is intermediate amplitude.
Okay.
So you see pairs, but just less.
Okay. Thank you.
Okay, so I think that we shouldn't ask more questions because we have to proceed to the next lecture. So thank you, David, once more.
Well, thanks a lot.